So there's really a lot of work that's being done on XAI. For example, if you think of techniques like LIME and uncertainty, which technical people really understand, but it's not always clear to social scientists on what to do with the outcome and the objectives of XAI. So there's really a gap between the explanations that the XAI technicians generate and the questions that actually gets asked by social scientists. And for that reason, we propose a multidisciplinary approach to consolidate these explanations that we generate by XAI and how to interpret these explanations along the guidelines of the expertise of social scientists. Because it's not our job as technicians to decide on what is fair, accountable, and transparent. It's our job to provide the tools in order to do that. And in this specific project, we show how a specific XAI technique called most relevant explanation is actually an appropriate metric to evaluate fairness and accountability, because it can allow for comparison of competing explanations and alternative reasoning. And from the social side, we take notions from Aristotle's ethics and from restorative justice in order to define fairness and accountability. And this is really a concrete demonstration of how the tech community can heed the call for recognizing that we need a multidisciplinary or a social technical system approach in order to translate and transfer the explanations generated by XAI to social scientists and to the end user. What is really important, what you just need to keep in mind, is that this is just one world view that we present here, but it's definitely not the only one. So when we decided on how we want to define societal harm, we choose to focus on representational harm and allocation harm. But of course, there are many other ways to define harm, and this is only one worldview. So when we think about societal harm from AI, then we can define it as representational. And this is more a social and cultural harm focused on social attitudes and traditions. And it's typically along the lines of identities such as race, class, and gender. And it's long-term, it's not easily quantifiable, and it's very subtle and therefore been neglected in the context of machine learning. So examples are stereotyping, recognition, exnomination, and underrepresentation. And then we also have harm from allocation, and that is more economically related. So that is where you, for example, don't get a loan, or you don't get insurance, for example. So you are excluded from some decisions, and you're not allocated something of economic value. And of course, in AI, there's the call to alleviate these harms. And we focus on FAT-ML in order to heed to these calls. And just a quick explanation or a quick definition of fairness, accountability, and explainability. So fairness refers to accessibility and reusable data, and it's typically where we have structural bias embedded in data related to gender, race, ethnics, etc. And we need to understand this bias and the consequences of actions based on the outcomes generated by these systems in order to have fair ML. Transparency is more about the system visibility. So it relates to understanding how ML systems are designed and developed. And transparency is what we call passive explanations because it's inherent in the model itself. So you get black box AI models and you get more open models, and the black box models are not transparent, and some statistical models like the one that we use are transparent. So transparency is about the system visibility, and explainability is about understanding the outcomes of these systems. Lastly, we look at accountability. And accountability is obviously where someone needs to take responsibility for the outcome produced by the machine learning system. And the ethical question that we have is, should there be blanket disclaimers of liability allowed, or only for systems that affect human lives directly? So that is one example of accountability. So, as I said earlier, there's sometimes or many times a gap between the explanations generated by the tech side and a tech system and the calls from end users. And the question is, what are end users really interested in? Are they interested in the maths? Are they interested in how the explanations was generated? And that's not what they are interested in. They want to understand the outcomes that's generated. And the possible impact of machine learning generated outcomes and the predictions on the end users and the broader civil society. And for that reason, we focus on post-hoc explanations to show the possible social impact of machine learning generated outcomes. So post-hoc explanations don't influence the specification of your models itself. So you don't need to compromise on the predictions of your model. It's completely agnostic from the model. So one might argue that in order to address fairness, one needs to look at the input data to the AI system. But it's almost impossible to enforce fairness on input data. And as many AI technicians might know, is that we tend to find proxies if we decide to omit certain sensitive variables. So it's easy to find an economic or a location proxy for an economic variable, or maybe also a location proxy for a gender variable or a race variable. So it's kind of like you can't avoid unfairness when it comes to input data. And for that reason, we rather focus on fairness on the model output. So to understand the fairness of predictions or decisions. Now the question is, what is a good explanation? A good explanation should address the objectives of the explanation task. And the explanation itself has value in its ability to advise end users with information about the model, where it's necessarily apparent in the predictions. And what we also say is that a good explanation should be precise and concise. So the precision judges the accuracy and the correctness of the explanation. The conciseness ensures that the explanation does not burden the end user with unnecessary information. So it does not contain variables that are not needed for the validity of the explanation. So in our mind, explanation should be precise but also concise. Before we carry on with explanations, I'm just quickly going to talk about the modeling technique that we use. And we use Bayesian networks, which is in this case quite a unique and special modeling technique because it's also by design very transparent. So by using a Bayesian network, we not only have access to post-hoc explainability, but also to passive explainability because of the transparency and of the Bayesian network. So just briefly, what is a Bayesian network? It's a graphical structure and it consists of nodes and directed arcs between the nodes. And the connected nodes actually is quantified by the strength, or quantified by conditional probabilities, which represents the strength of the dependencies that we have. And a Bayesian network is really very flexible when it comes to the type of reasoning and inference that you can do with it. So you can do predictive reasoning, which most models can do, just to say what will happen. But you can also do diagnostic reasoning to say what went wrong. You can do explanation and also counterfactual reasoning. An example of counterfactual reasoning is how do I make something happen? Or it's another example is also intervention, to say, if I did X, would my outcome be different? So those are the type of really strong and powerful counterfactual reasoning examples that you can do with a Bayesian network. Now, I'm very briefly going to explain most relevant explanation as an explanation technique. So most relevant explanation can be applied to other modeling techniques as well, but it's really very well suited for a Bayesian network because we have access to the full joint probability specification of all the variables in a Bayesian network. Most relevant explanation explains the current state of an observed variable with reference to the target variables in the domain. So the observed variable is presented as evidence and the target variables is the explanatory variable of interest. The foundation of MRE is the generalized Bayes factor, and the log of the generalized Bayes factor is known as weight of evidence, and it was actually used by Alan Turing in the Second World War to break the Enigma code. And I'm going to give a very simple example. Say, for example, you have a product recommender. And your evidence is that you have a high income shopper profile. And you want to know what is the most relevant explanation for this evidence, the evidence of having a high income shopper profile. And your hypothesis one is that this shopper bought bread. And hypothesis two is that the shopper bought artisan cheeses. So you have the odds of buying product H, which can be bread or artisan cheese, among shoppers like the evidence, which in our case is a high income shopper profile. And you can now calculate the odds ratio for each one of these hypotheses. And basically, when you contrast these two hypotheses, then the higher odds ratio will then be your most relevant explanation. So in this case, we can see that the odds ratio to buy artisan cheese, given the evidence of having a high income shopper, will be much higher than when this shopper buys bread. Okay, so now I have explained the technique, most relevant explanation. And what is important to know about most relevant explanation, that it is both precise and a concise explanation. So you don't end up with irrelevant information in your explanation set. You can also, you have a set of explanations. So you don't only have one explanation, but you have a set that you can choose from. And you also have guidance on the actual value of the generalized Bayes factor to know if that specific explanation is significant or not significant. So let's go back to fairness. So now we are on the social side again, and now we say, okay, we have an XAI technique, but it's not my job as the technician to define fairness. It's the job of the social scientist to define fairness. So in this case, my colleagues decided to define fairness along the notions of Aristotle's theory. Because the goal of fairness is to ensure that decisions are devoid of discrimination. But what is also important to realize is that if we if we just want an even distribution, then why do we need a machine learning technique? At the very essence of machine learning is the fact that the algorithm does distribute goods unequally. So we need to work with that. And that is where Gandhi came up with the idea of using notions from Aristotle, the theory allowing for discrimination on certain characteristics. So to consider what the relevant merits are in the context within which we are distributing and allow for discrimination based on certain merits. And how can such an approach be reconciled with machine learning practices? So we asked the machine learning algorithm to define what the relevant characteristics are in this distribution of goods. So in other words, to predict or to decide. So, and this is where the explanation comes in. So we basically, with XAI, with explainable AI, we actually get an explanation for the outcomes of the machine learning algorithm, which is this distribution of the decision. And the social scientists should consider which variables are completely, we call it unhonorable in this given context. So for example, in a society that is striving for gender equality, gender is a variable we do not wish to give merit to in a job allocation. And we can then actually identify variables in a posthoc explanation. So MRE provides explanations that facilitate consultation between the XAI technicians and social scientists, because it lists variables that were relevant in the final decision. And if you don't see the unhonorable variables or proxies in the explanation set, it is very encouraging that we have a fair machine learning system. And again, like I said previously, MRE is a posthoc explanation technique, which means that we negate the issue of model overspecification. For accountability, we said that the appropriate way to respond to injustice is restorative justice. And we always have two parties in every act of wrongdoing. We have a transgressor and the person that is wronged by this wrongdoing. And the focus that we have is on the wronged person and how to address their experience and not on who to punish. And one example of that is for machine learning, we want to know how to restore justice to persons who were wrongly, say, for example, not assigned bail, not given a loan, or stopped and frisked by police based on their race. And we use a restorative justice framework of truth commissions, because truth commissions actually gives you a platform for wrongdoers and victims to express their truths, and also for transgressors to explain and acknowledge each of their wrongs. And we acknowledge that truth commissions are much more complex than what I now just explained, but the concept stays the same. So let's look at how MRE can facilitate accountability. So to account for Bayesian network decisions, because remember we are using a Bayesian network, those responsible for it can turn to MRE. In the context of a Bayesian network, the truth of the outcome is an explanation of the decision or output, because that explains the decision. And the explanation set contains variables most relevant in the making of the final decision, whether that decision was morally right or wrong. The MRE answers the question of why that decision was made. And this enables the context of trust and learning from harmful decisions. So it assists in correcting the harm done, because if you can explain and why this decision was made, why this harm was done, then you can actually assist in correcting the harm done. So it gives feedback to your machine learning model, or in this case, to your Bayesian network model. Furthermore, MRE is concise and precise, which means that the explanations are correct and without irrelevant information. So it becomes a safeguarder against opacity and in terms of possible harm from the relevant systems. And this overcomes the weakness of truth commission frameworks, which this weakness is that there are many truths in a truth commission. So with preciseness, we overcome this weakness while allowing moral learning in respectful contexts. So the MRE provides a context within which there is acknowledgement of the harm and an explanation of it. So what we've shown in this work is specifically one configuration and one worldview of socio-technical collaboration to address concerns of critical machine learning. And on the technical side, we introduce most relevant explanation as a suitable post-hoc XAI technique. And on the social side, we first defined harm as representational and allocation harm. And secondly, we showed how MRE and the social and ethical concerns around possible harm can be brought into conversations such that the model can be adjusted if needed and possible harm can be addressed. The lessons learned from this is first is just that this is not easy. To have a true multidisciplinary collaboration takes a lot of effort. It takes a lot of honest conversations. And just one example is terminology. What XAI technicians view as post hoc is something completely different than what social scientists mean by post hoc. It's kind of like there's a lot of loaded terminology that needs to be sorted out. So it was really an exciting project, and I think something that we are really all proud of in our team. But And also very important, like we said, just to facilitate the discussions around what XAI technicians can bring to the table, and how social scientists need to define ethics, and how XAI can address those definitions. And the only way to do that is to have a truly multidisciplinary collaboration. Thank you.